Hi everyone, in this video, in this chapter, we're going to be talking about estimating the value of a parameter. Specifically in this one, we're going to be estimating a population proportion. So our first objective is to obtain a point estimate for the population proportion. So a point estimate is the value of a statistic that estimates the value of a parameter. So for example, the point estimate for the population proportion is p hat, we've seen this before, which equals x over n. And remember, x is the number of individuals in the sample with a specified characteristic, and then n is the sample size. So let's take a look at this one here. The Gallup organization conducted a poll in which a simple random sample of 1,015 Americans, 18 years or older, were asked, do you consider the amount of federal income tax you have to pay is too high? Of the 1,015 people surveyed, 458 of them said yeah. Obtain a point estimate for the proportion of Americans 18 and older who believe the amount of federal income tax they pay is too high. Okay, so we're just going to substitute into our formula. The people that had the characteristic of too high for tax is x. The sample size was our 1015. And we just divide, and that's our p hat value, 0.451. And so we estimate the proportion of Americans 18 years or older that believe the amount of federal income tax they have to pay is too high is about 45.1%. Next, let's construct and interpret what's called a confidence interval for our population proportion. So in statistics, we construct an interval for a population parameter based on a guess along with a level of confidence. So we have a guess, but then we also add to that a level of confidence for our guess. The guess is the point estimate of the population parameter, what we just calculated, and then the level of confidence plays a role in the width of the interval. So notice the longer the width of the interval, it's a higher level of confidence. The lower the width, smaller the width, it's a lower level of confidence. And then notice our guess is here. If you just kind of think about this visual, we're saying this is our guess, but we could have anything within this interval be the actual value. That's what this visual is trying to tell us. So a confidence interval for an unknown parameter consists of an interval of numbers based on a point estimate. And then the level of confidence represents the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained. So the level of confidence is denoted as follows. It's going to be 1 minus alpha times 100%. So we have our confidence interval, and then we have our level of confidence, which is going to be a percent. Notice from this calculation. So for example, a 95% level of confidence, this would mean that alpha is 0.05. If you plug that into our calculation that we just looked at, that'd be 1 minus 0.05 times 100%. This implies that if 100 different confidence intervals are constructed, each based on a different sample from our population, we would expect 95 of the intervals to contain a parameter and 5 to not include the parameter. Okay, so our guess is the parameter, and with such a high confidence level, we're saying 95 out of our 100 samples should have this parameter in it. So let's review some things that we've learned previously. And this is about the model that describes the sampling distribution of p hat, which is our sample proportion. So p, remember, is our population proportion, but p hat is our sample proportion. So we've talked about this before, but let's discuss it. The shape of the distribution of all possible sample proportions is approximately normal, and this is true if this calculation is greater than or equal to 10, which is the sample size times our population proportion times its complement. And then also the sample size should be no more than 5% of the population. That's because that lets us know that our values are independent, as long as we have a sample size less than 5% of the population. And then the data has to be randomly obtained. So we want all these three things to be true, and then we can say that our distribution is approximately normal. Also, we learned that the mean of the distribution of the sample proportion is actually just equal to our population proportion. So P, our population proportion, is the mean of our sample proportions. And then also we learned that the standard deviation of the distribution of our sample proportion, which also was called the standard error, can be found using this calculation. So sigma sub p hat is square root of p times its complement divided by n. So because the distribution of our sample proportion is approximately normal, we actually know that 95% of all the sample proportions will lie within 1.96 standard deviations of p. So just real quick how we got that. So notice our normal curve here. If we know that our confidence interval is 95%, that means what's remaining is 5%. So if we split that up between the tails here of the area under our normal curve, then what you would do is you would say you're looking for your z value, your z-score, with the corresponding area to the right would be 0.025 for 2.5%. And that, if you go to your table for standard normal distribution, that will give you that 1.96 for the corresponding x value. So that's where the 1.96 came from. This is close to the empirical rule, but if you recall, the empirical rule says 95% of the data is within 2 standard deviations. So this is close to 2 standard deviations, but just a little bit less than that. And so 2.5% of the sample proportions will lie in each tail. So that remaining 5%, 2.5% of it's here, 2.5% of it's here. So this is saying, like, out of all the samples, 95% of them will have P within them, within that interval, and only 5% P will be somewhere out here. So it's common to write confidence interval estimates for the population proportion by doing the following. So we say our point estimate and then plus or minus our margin of error. So the margin of error for a 95% confidence interval for the population proportion is the number we were just talking about, 1.96 standard deviations. This determines the width of the interval. So to visually illustrate this confidence interval, let's take a look here. We're drawing our sampling distribution of p hat, and then we create a slider that shows our p hat minus 1.96 standard deviations, and then our p hat plus 1.96 standard deviations. And then as p hat leaves our blue shaded region here, the corresponding confidence interval does not capture the population proportion. So that's this slider thing down here. So notice our population proportion is right here in the center. We have p plus 1.96 standard deviations, plus or minus, so to the left would be minus. And then if we start adjusting, if we say our p hat is less than p, then this interval here is like, think of it just like slid over to the left. If p hat is like way further down here, way to the left, notice that no longer is our original population proportion even within this interval at all. So the figure tells us that for 95% confidence interval, 95% of all sample proportions will result in a confidence interval that includes the population proportion. And while only 5% of all sample proportions, which happens to be those in the tail, will result in a confidence interval that does not include the population proportion. So that's what's happening with this blue one here. So 95, this was this idea of 95 out of 100 samples will have an interval where P is still inside that interval. So notice, even though we're down here in the red, this interval, P is still in there. It's still in between the two red brackets. But 5%, or 5 out of 100 of those samples, it would be maybe over here or over here. The P, our population proportion, no longer is actually within this interval. So that's this idea of our 95% confidence interval. 95% of the samples, P will still be within this interval if we slide left or right. So let's take a look at this one. We're going to illustrate what 95% confidence means and a 95% confidence interval in another way. So we're going to simulate obtaining 200 different random samples of size 50 from a population where our population proportion is 0.7 or 70%. Okay, so let me show you how to do this in StatCrunch real quick, and then we'll talk about what it's indicating. We'll interpret this. We're going to go to applets, and we're going to go to confidence intervals for a proportion. Okay, and we want P to be 0.7 in our example, and our confidence interval is already here at 0.95, and we actually want 200 samples. Okay, and that's all we really need. We're going to hit compute. And there it is for us. Okay, so that's how you do it in StatCrunch. So now let's talk about it a little bit. Okay, so we're going to see this on the next slide, that we have a confidence interval in intervals in groups of 100. And so a green interval is going to be a 95% confidence interval that includes P, our 0.7. And then anytime we see the red interval, it's a confidence interval that actually doesn't include P. Notice that the red intervals do not capture our p-value, 0.7, and have centers that are too far away. They're actually more than 1.9 standard deviations or standard errors away from p. So of the 200 confidence intervals obtained, 10, which are the red intervals, do not include the population proportion. So let's take a look at that. So we have just a few of the red ones here. Let's spread out all the 200. There's 100 here, 100 here. And so notice if P is right here in the black line, 0.7, look at all the red ones. This one's too far to the right. It doesn't actually include P, or in this case, think of it like touching P. Red here is too far to the left. This one too far left. This one too far right, and so on. And so the green ones, they're an interval that overlaps with P, in this case 0.7. And so anything that's too far to the right or left doesn't include our p-value. And so, for example, the first interval to miss has a sample proportion that is too small to result in an interval that captures 0.7. The second interval to miss has a sample proportion that's too large. That's to the right. The too small was to the left. And so 190 out of the 200 samples is equals our 0.95, or 95% of the samples have intervals that capture the population proportion. So a 95% level of confidence means that 95% of all possible samples result in the confidence intervals that include our parameter. In this case, it was 0.7. And then only 5% of the samples result in a confidence interval that don't include that. Now, a caution to be aware of. A 95% confidence interval doesn't mean that there's a 95% probability. So this is not the same as probability, that the interval contains the parameter. So remember, probability describes the likelihood of undetermined events. So therefore, it does not make sense to talk about the probability of the interval that the interval contains the parameter, since the parameter is a fixed value. So another way to think about it, if I flip a coin and obtain a head, if I ask you to determine the probability that the flip resulted in a head, it would not be 0.5 because we already know the outcome. Instead, the probability is 0 or 1. It's 1 if I got heads, and you already knew that. Confidence intervals work the same way because P or mu are fixed quantities whose value is unknown. We do not say that there is a 95% probability that the interval contains P or mu. Instead, the probability that the interval includes the parameter is either 0, meaning it doesn't include the parameter, or 1 if it does include the parameter. Okay, so whether a confidence interval contains the population parameter depends solely on the value of the sample statistic. So any sample statistic that is in the tails of the sampling distribution, like we saw the tails under our curve, will result in a confidence interval that doesn't include the population parameter. So remember this calculation, 1 minus alpha times 100% is going to be our percent of all sample proportions that will result in a confidence interval containing our population proportion. The sample proportions that are in the tails of the distribution in the figure here will not result in confidence intervals that contain the population proportion. So this is sort of generalizing what we saw earlier. We had under our curve here in the blue, we had within 1.96 standard deviations, greater than and less than our population proportion. But that was for a specific 95% confidence interval. So this is saying in general. So we have to determine A or alpha for 95% confidence. That was 0.05. That was alpha. So depending on the confidence interval we're trying to calculate, we're just going to adjust our values down here as far as this number times our standard deviation. And so the tails over here, that's going to be alpha divided by 2 times 100%. And so that's how you're going to get the samples that don't contain your population proportion, the percent of them. So the value z sub alpha over 2, we call this a critical value. We've actually seen critical values in the past, but this is our critical value of the distribution. It represents the number of standard deviations the sample statistic can be from the parameter and still result in an interval that includes the parameter. So here's a table that shows some of the common critical values used in the construction of confidence intervals. So notice the higher levels of confidence correspond to higher critical values. So like 95%, each end of the tail of here under your curve here is 0.025, which is 2.5%. And the corresponding critical value for that would be 1.96. For 99% confidence level, we have each area under the tail to be 0.005, which is 0.5%, so very small number. And here's a corresponding critical value. So from here, we could get, you kind of use your critical values. You have a critical value table a lot of times, but let's say you wanted to use your standard normal distribution table. You would start with knowing your confidence level, calculating alpha over 2, and then that's the area. And then you go to your z-scores, you look in the table for that area, and then you find the corresponding z-score. But just a quick note, this is going to line up with a negative z-score because remember, the table gives you the area to the left, and so if you want, you could just change that to a positive number for it to be the critical value, or like we've done in the past, say 1 minus the area, and then look for that area in your table to get the z-score. So interpretation of a confidence interval, a 1 minus alpha times 100% confidence interval indicates that 1 minus alpha times 100% of all simple random samples of size n from the population whose parameter is unknown will result in an interval that contains the parameter. This is the same thing we've kind of been saying over and over. This confidence percent tells us how many of our intervals, if you think of out of 100, would contain the parameter. So a 90% level of confidence doesn't actually tell us that there's 90% probability. Remember, it's not the same as probability. It's telling us just the level of confidence, or that 90 out of 100 samples would contain our parameter. So next example, when the Gallup organization conducted the poll introduced in the previous example, 45.1% of those surveys considered the amount of federal income tax they had to pay was too high. And then Gallup reported its survey methodology as follows. Results are based on telephone interviews with a random sample of 1,015 national adults aged 18 and older. For results based on the total sample of national adults, one can say with 95% confidence that the maximum margin of sampling error is 4 percentage points. So let's determine and interpret the confidence interval for the proportion of Americans aged 18 and older who believe the amount of federal income tax was too high. Okay, so the point estimate is 0.451. That's our parameter value. And we're told the margin of error was 4%, so that's 0.04. And so what you do for your confidence interval is you just add and subtract the margin of error. So we have our 0.451 minus 0.04, and then 0.451 plus 0.04, and that gives us a lower and an upper bound for our confidence interval. So what we can say is we're 95% confident that the proportion of Americans aged 18 and older who believe that the amount of federal income tax they paid was too high is between 41.1% and 49.1%. So when you're constructing a confidence interval for a population proportion, here's in general how you can get your upper and lower bounds. So remember, n is your sample size, and then for alpha, depending on the confidence interval you're seeking to get, you have that value you plug in. P is your population proportion, and then P hat is your sample proportion. And so notice what this is. It looks a little mathy, but it's just the same thing we just did. You have your parameter value, and then minus the standard deviation. The square root is the standard deviation times your z-score. Same thing here, your upper bound, your parameter value plus your standard deviation times your z-score. So this is your sample proportion plus and minus. This is actually the margin of error, or some amount of your standard deviation. And so just a note, it has to be the case that n times p hat times its complement is greater than or equal to 10. And this right here is just saying that our sample size has to be less than or equal to 5% of the population. And so the margin of error is that calculation that we add and subtract to the population proportion. So we had seen this in just the previous slide, but we have our margin of error is z sub alpha over 2 times, this right here is just your standard deviation, square root p hat times its complement over n. So let's try this out. In the parent-teen cell phone survey conducted by Princeton Survey Research Associates International, 800 randomly sampled 16 to 17-year-olds living in the U.S. were asked whether they have ever used their cell phone to text while driving. Of the 800 teenagers surveyed, 272 said that they did. Obtain a 95% confidence interval for the proportion of 16 to 17-year-olds who text while driving. Okay, so we're going to do this in parts. Step 1, X is 272. That's our successes. And so remember, success and failure is just the characteristic is true for success, it's false for failure. And so out of the n, our sample size of 800, so our p hat value, our sample proportion, is just the 272 divided by 800, or 34%. Then next, we want to verify that this is going to have our nice approximately normal distribution. So let's verify a few things. N times p hat times its complement, plug in our values. Because this number is greater than or equal to 10, that's good. And then also, we want to verify that our sample size is less than 5% of the population, less than or equal to. And it definitely is, if we've only sampled 800, out of about 1 million teenagers of that age in the US. So that means that our sample values are independent. Now, because we're wanting a 95% confidence interval, in that case, alpha is 1 minus 0.95, which is 0.05. Okay, and so that's our alpha value. And so to get z sub alpha over 2, we plug in that 0.05, and we're looking for z sub 0.025. And from our table, and we've seen this one before already, we're going to get that equals 1.96. So I just want to show you real quick on the table. I've been mentioning it, but just a reminder how this goes. We already know the area under the curve to the left of this z value. So what we're looking for is inside the table here. We're looking for 0.025. Let's see. It's going to give us this one, looks like right here. Okay, so 0.025. And notice what that lines up with. It's going to be, if you go left, negative 1.9. And if you go up, 0.06. So that's negative 1.96. And so our value is going to be 1.96. But just real quick to show you how to get the positive value, you actually do the complement of this if you want the area to the right. So remember, this gives you area to the left of that z value. So if we want the area to the right, like the right tail, we'd say 1 minus 0.025. That's going to give us 0.975. So let's look for that on the table. And 0.975 is right here. Okay, right there. And that lines up with 1.96. So just a quick reminder on how to do that. So then we're going to substitute into our formula. N is 800, and we'll get our upper and lower bounds. So our formula for lower bound is when we subtract the z-score times our standard deviation, and that's going to give us, after plugging in all of our values, 0.307. And so for the upper bound, very similar, but we add the standard deviation times the z-score. That's going to give us 0.373. And so the margin of error is 0.033. That's from this part right here, multiplying this 1.96 times our standard deviation. And so we can say we are 95% confident that the proportion of 16 to 17-year-olds who text while driving is between 30.7 and 37.3%. So now let's do the same thing, but we're going to use some technology. So X is still, the number of successes, 272, and is still 800. So P hat is 0.34. Okay, we still check for independence and that our sample is random. And so now let's go ahead and go over to StatCrunch and compute. Okay, so we're in StatCrunch, and we are going to go to Stat, Proportion Stats, and one sample, and we're going to go with Summary. Okay, now once we're there, we had 272 successes out of our 800 observations. And so then we want to go ahead and click our confidence interval. We want 95%, and that should be good. Compute, and there we have it. So that's how we get these values in StatCrunch. All right, so here's what we got. Our sample proportion was 0.34, which we have figured out by hand. We have our standard error, our lower bound or lower limit, and our upper bound or upper limit. And so this is the same values we got by hand, if you recall. And then the margin of error, you still can do your calculation for that by saying your lower or upper limit and then adding or subtracting the sample proportion. That's how you can get that 0.033 that we got earlier. And so in step 4, we say we're 95% confident that the proportion of 16 to 17-year-olds who text while driving is between 30.7 and 37.3%. All right, so the effect of level of confidence on the margin of error. So we stated earlier that logic suggests that a higher level of confidence leads to a wider interval, if you remember that visual we had seen toward the beginning. So for example, the problem estimating the proportion of teenage drivers who text, let's determine the effect on the margin of error by increasing the level of confidence to 99%. Okay, so with the 99% level of confidence, alpha is going to be 0.01. That's just 1 minus 0.99. And then to compute our margin of error, let's first determine the value of z sub alpha over 2. So that's going to be z sub 0.005. So from your table, you figure out that that's going to be 2.575. Now we're going to substitute our values into our formula. And we have still that p hat is 0.34 and is still 800. And now we have our standard deviation here times this different z value, so 2.575, giving us a margin of error of 0.043. Okay, so you can use technology to get this as well if you use a TI-84 calculator. So let me show you how to do that real quick. Okay, so we're going to hit Stat, and we're going to go to the right to Tests. And I'm going to go down to A. So I'll just show you, but you can just click A to get there faster. It's a little laggy, so give it a second. One more maybe. Okay, so A is for 1 proportion. Okay, and we're going to enter our values. I've already done that. X is 272, N is 800, and our confidence level is 99%. So we go down and hit Calculate. And there we have it. So it gives us our lower bound and our upper bound, our p hat value, and that's how you do it on the calculator. All right, so our lower bound is given, our upper bound is given, and you can find p hat by taking the average of those two. Actually, that's another way to get 0.34. And then our margin of error is just our p hat value minus our lower bound, or you can say your upper bound minus your p-hat value. And so the margin of error for 95% confidence, we found it to be 0.033. So increasing the level of confidence increases the margin of error, resulting in a wider confidence interval. So the effect of sample size on the margin of error. How does this sample size affect our margin of error, essentially? So we know that larger sample sizes produce more precise estimates. This is something we learned a long time ago, the law of large numbers. So given that the margin of error is this calculation, our z-score times our standard deviation, we can see that increasing the sample size n decreases the standard error. So the margin of error decreases. Basically, by making this denominator larger, this is going to decrease. So this means that larger sample sizes will result in narrower confidence intervals. So next objective, let's determine the sample size necessary for estimating a population proportion within a specified margin of error. So this time we're going to be given a margin of error that we're trying to stay within. So sample size needed for a specified margin of error, which is capital E, and our confidence level, 1 minus alpha, is going to be n. So n is a sample size. Normally we've been starting with n, like we know that we're sampling 800 people or whatever the number may be. This time we're calculating n based on these values of p hat, its complement, our z-score, depending on alpha, over the margin of error, E, and then that quantity gets squared. So we're calculating our sample size. And so the formula uses p hat, which depends on n, the quantity we're trying to determine. So it gets a little tricky. So two possible solutions for this. One, use an estimate of p hat based on a pilot study or an earlier study. Or two, let p hat equal 0.5, which gives the largest possible value of n for a given level of confidence and a given margin of error. Okay, so by default, we can either use something from the past that's been done in terms of that same type of study, or we use p hat equal to 0.5. And so our sample size needed for estimating the population proportion p. We have our confidence interval, 1 minus alpha times 100%. For p, our population proportion, and our margin of error E is given by this calculation we saw just a moment ago. And then we'll round up to the next integer, okay, where p hat is a prior estimate of our population proportion p. So remember, p hat is our sample proportion. If a prior estimate of p is unavailable, then the sample size required, we get a 0.25 here. So that's because if we go back, that's going to be 0.5 times 1 minus 0.5. And that's the default one that we use if we don't know what p hat is. And that's where 0.25 comes from. And so the margin of error should always be expressed as a decimal when using these formulas. So let's try this example. An economist wants to know if the proportion of U.S. population who commutes to work via carpooling is on the rise. What size sample should be obtained if the economist wants an estimate within 2 percentage points of the true proportion with 90% confidence if the economist uses 2009 estimate of 10% obtained from a survey. And then we'll do a part B in just a minute. So E is going to be 0.02, that's our 2%. And then our z-score is, for alpha in this case, it's 0.1 because we're looking for 90% confidence interval. So the 0.1 came from 1 minus 0.90. And so we want z sub 0.05. That's going to give us this value of 1.645. Okay, so E was given, it's 0.02. Z, we just did a little bit of calculations from the given alpha, or the given confidence interval. And then we substitute those numbers into our formula for n. Remember, we're trying to find the sample size here. So we plug in the 0.10, and that's going to be from the previous study that we were told about from the 2009, the complement of that, plugging in our z-score, and the margin of error. Remember your rules of arithmetic and order of operations. So you're going to do this division first, then square that value. Do this subtraction, and then multiply all three of those, and you're going to get 608.9. So we round this up to the nearest integer, which is 609. And so the economist must survey 609 randomly selected residents of the United States. So now the economist is not going to use any prior estimates. So by default, we use 0.5 for p hat, which when we plug that into our calculation, remember that gives us that 0.25 value. E, our margin of error, is still 0.02. Z sub 0.05 is still 1.645. So we just plug those numbers in, and we get 1,691.3. Rounding, we get 1,692. So the economist must survey 1,692 randomly selected residents. And so the effect of not having a prior estimate of p is that the sample size increased by quite a bit. It was more than doubled from knowing a prior p value. Okay, so that's it for this one, and thank you for watching.